Hello. So this is a shorter presentation style to some of the others. So to try and keep you to wake you all up after the morning session, it's going to be a bit faster paced. I'm going to be talking about asset management for continuous assets. So when I say I'm going to explain a little bit about the principles behind what asset management is away from the railway, and then a bit on what a continuous asset is, again, trying to bring it in and apply it to permanent way, but also trying to keep it apart as well. So first of all, what is asset management? So asset management in its simplest form is working out what asset is needed to allow the organisation to fulfil its role, then working out the most efficient way to keep that asset working, then working out when that asset needs to be disposed of, and finally, who is going to do what at what point. This is very straightforward when you have one or maybe two assets. So what is a continuous asset? So a continuous asset, in railway terms, is an asset that can be drawn as a line over a geospatial area unbroken. Examples are track, OLE, cable troughing, earthworks. How is this different to a discrete asset, though? Discrete assets can be put as a point on a map, a node. Ultimately, they can have multiple components, but they're in one place. Examples, bridges, signal posts, etc. Why is this distinction important? It's important because in a continuous asset, your fault can be anywhere along that line. You don't know where it is, it might appear anywhere. Now, one way we can overcome this is by splitting that continuous asset into discrete parts. We do this by calling them eighths, which means it's very the problem is you can still have hundreds of eighths to look at, so it doesn't exactly overcome the problem of having a problem anywhere along that line. Now, the way we currently view this is through trace. So trace illustrates the current track performance at every point along the track. Now we can use subsequent trace, and then we can add subsequent trace to this, and we can see how that track is performing over the next 2 months. Now, if we turn the trace on its side, you get the graph at the bottom. The graph is the thing you notice is that graph looks different everywhere along that piece of track. That is called the P2F curve. So the P2F curve provides a curve indicating the performance of an asset over time. If this curve is known, you can apply your risk appetite. So your risk appetite is the point where you are willing to no longer take the risk of what might happen to that asset. So you could set it at any level along that performance degradation curve. If you know this curve, you can plan your maintenance activities far in advance. You can use, if you know it's going to fail at that point, the better you know this curve, the earlier you can predict it, the earlier you can plan. It would be near impossible for a human to look at every single point along a continuous asset. You can prioritize where you would look to try and predict this and work out where it is, but it would be near impossible for it. So is there a way in which we can predict that model? So it's a physics-based model. One, this takes engineering principles and establishes a rate of deterioration. An example of this, in some ways, is TrackX. You've also got all the way through to your Euler-Bernoulli model. These tend to be not accurate enough and to be useful. You've then got statistics condition-based models. So this takes all your data points, puts them into one place, and then tells you, at this point and this piece of track at this time, this is what happened. The problem with that is that you then struggle to apply this everywhere. So you then get onto the knowledge-based model. This combines the two and allows you to apply the broad understanding that the physics base gives you to everything else. And this is where machine learning comes in. Machine learning, simply put, is when a computer learns how data points link together. Given enough data, it can then start working out what's going to happen next. Now, a human can do this already. But as I've already highlighted, the problem with a continuous asset is they can't do this everywhere simultaneously. So how can we apply machine learning? Well, if you give a computer a string of data and tell it how that data links together and then gives it an output at the end, it can, let's say, machine failure, it'll then start picking up patterns. Now, at the beginning, it'll pick up every pattern. But as it goes along, it then starts to pick up the regular patterns. And it tests it again and again and again and again and again. The more a pattern has a positive feedback loop, the more likely it's going to work. So the first level of it is using one metric. So one metric might be top, for example. You give it all your variables, so your different types of train, your velocity, how your track's responding, all of these things. This is quite simple in comparison to other forms. Next level is combining those multiple metrics together. Taking your alignment, your top and your side wear, all the thing that it already did, putting them together into one place and going, if this happens here, it might mean you have a problem with a different element over here instead. This form of machine learning requires far more processing power, so is not necessarily as feasible right now, but it is definitely where the world is going. So what does this mean ultimately for us? Ultimately, this is where risk-based maintenance is going towards. It is producing a proactive maintenance strategy. This gives you a list of where the problems are and when they will fail. The advantage is that the earlier you know that, the better you can plan your maintenance. So you can have boots on the right ballast. Not boots on ballast when you need to react, but boots on the ballast in advance when you know they need to be there. This also gives you, produces on so you get to your proactive planning instead of reactive planning. And this is the key behind all of this and where we're going with all these things that have been worked on. Ultimately, at the moment, we don't have enough data points for this to be working in its most fluid motion, but it's going in that direction. Thank you ever so much.